All right, so what we're going to talk about in this video, it's the second part of the last video really. It's called Transformers, goes along with that last video. Uh, these things are definitely, I could say my corny, definitely more than meets the eye kind of joke here. But different kind of transformers here. Before we get going on this, we started talking about, we had DC current before, we had from cells and batteries, and now we're on to generating power where we generated AC current, alternating current from instead of direct current. And so just real quick before we get going, in DC our power sources were like this, right? They were that, and that was a cell. So this was for DC. For AC, it's a little different because we don't just have this. This is just direct current. For AC, it's pretty much what you would think. You just, it's pretty. You look at it and you'd think, oh yeah, it's alternating current. It's just that with a little sine wave drawn on a little wave for it alternating back and forth. And that's our symbol for an AC source of power. And we need that here to be able to do the transformer. So now we've talked about inducing current. We've talked about inducing EMFs, right, through changes in flux and things like that. So now what we want to do is actually have the flux from one circuit create a flux in another circuit. And so let me show you what I mean by that. And this is called this is something called mutual inductance goes along with this. We're inducing currents from one current. So what we're going to do is start with an alternating power source here. There's our little alternating power source. And what we're going to do is set this up and we're going to run it through a coil of wires. Okay, just a big coil of wires like that, and that's it. And this is going to be our primary. It's our primary circuit, our primary source, our primary coil. And then what we're going to have is our secondary coil, and we're going to set it up. And now this isn't the best geometry that I'm showing you here. This is just to illustrate the basic idea. And then we can put something that uses up voltage here, a voltmeter or some sort of object that's going to use this up. And what we're going to do is as we run alternating current through this one, it's going to go back and forth. It's going to create magnetic fields that go this way and then they go that way, right? As current runs one way, it creates a north on this end, and then when current goes the other way, it creates the north on this end. So it's going to flip-flop the fields. Well, these field lines, they're going to stretch out over into this guy. And like I told you, it's not the best geometry. So when this is pointed north, it's going to have a field going through this coil pointed that way. And then when this flips to south, it's going to have a field pointed this way through the south. And what you then get is you get a changing flux through this coil here, constantly changing, which produces an EMF. All right, so over here we're creating a field, and over here we're producing an EMF in this. Okay, and basically it's going to mirror back and forth. What this one does, it's going to mirror what this one does. So it mirrors this. This is called your secondary, and your secondary coil just mirrors what your primary does. Okay, and there, of course, again, there's better geometries we can set up to make this work better, but this was just the basic idea. You have two coils next to each other, and that's what they do. One of the ways we can actually make this better geometrically would be to take the two coils and actually put them next to each other. So you can have your alternating source here, come over here, put our coil of wires like that, and then hook that up, and then put our other coil of wires next to it, right? And then produce, our EMF from that. You can do that, and that will make it a little better. They're right next to each other, then they're closer together, and so the field produced by the primary here, I'm just going to put a P, will be mirrored over in the secondary one, and that works. And then you can make this even stronger. What we do is, and what can be done is you put what's called an iron core in there. So you put an iron core, not that these are shorted to it, but iron magnetizes real easy. So you wrap the coil around this edge, right? So you make like a loop of iron core, and you wrap the other coil around the other end. You don't short it, it's not touching it. But what happens is this creates a magnetic field, and it magnetizes the iron core. So now not only do you have the magnetization of that's produced by the coil itself, by the current running through the coil, but it's amplified by taking this iron and magnetizing the iron. So normally if you look at that hunk of iron, you have a bunch of regions. They're called domains, and in each domain you have a net magnetism, but they're lined up randomly like this. They're just kind of lined up, all these domains. When you magnetize it, what happens is all these domains that you have, I can't draw the exact same ones, but these domains, what happens is they all line up. So if I put it in a magnetic field, they all line up, and then they all line up. So if they're like this, all their own little magnetic fields are canceling each other out, and so there's no net magnetic field. Put it in a magnetic field that causes them to line up, and now not only do you have the strength of the magnetic field you put it in, but now all the magnetic fields of the iron are all lined up, and you have their magnetism adding on to the magnetic field you already had, and it amplifies it. So you do that sort of thing here, and then this iron core amplifies it, and it creates a stronger coupling between the two. So essentially what happens is you get what are called the little eddy currents that get produced inside here, and it lines it all up and just adds on to that, and it adds on to it. But so these eddy currents will occur in here too as the magnetic field goes through it. Basically eddy currents are a little response to it, where little currents will form inside the material itself. These little currents will flow in little circles in order to counteract the flux, because you also have to think you're changing the flux through the iron core, and that actually tries to then counteract the magnetization of this ordering of the cores. You get these little currents that produce counter magnetic fields that start to cancel it out. So it works pretty well. But one of the ways you can reduce this even further is not just to put a piece of hot iron in there, but to actually laminate iron. And so what that means is you take your iron core, see if I can draw this decently. So here's our iron that we're using, and you make a thin sheet of it. And then on the back of it you put a thin sheet of something that's not conductive, like saran wrap or plastic or something. And then that's, so you have an iron, and then you have a non-conducting thing, and then you have another iron sheet, and then a non-conducting sheet, and then an iron sheet, and you go back and forth alternating between this, and what you end up with is this iron laminate thing. You hook it all together, you sandwich them together, you glue them together, you hook them together, and that's what a laminate is when you do something like that. You may have heard it with like wood, like laminate wood or something like that, but it's a bunch of layers of iron, non-conductor iron, and you put them together, and then the laminate doesn't allow those little eddy currents to happen as much. It reduces these little circular loops of current because they can't flow across between the layers, and that reduces it, makes it even stronger there. So making a laminate iron core works even better. Very clever little idea, but anyway, that works too. Hopefully some of that made some sense there. Then what we can do is actually start to mess with the coil. So we've got this thing pretty efficient. We have our laminate core that magnetizes but reduces any of the little eddy currents that would try and undo it. So we've got the geometry down. Now what can we do with this? What's the point of this? Why would we just transfer voltage to another place and in what appears like not 100% efficient? We're definitely going to lose some no matter how well we make this laminate core. There's always going to be something that causes some loss. So what's the purpose of this? And what this is this allows us to change voltage. We can change voltages. Okay? And what we can have is we can have a step-up transformer, and this raises voltage. So the secondary raises voltage, so the secondary EMF is greater than the primaries. Okay, that kind of thing. It steps it up, and then we can have a step down. So that will lower voltage, and again here the secondary, though this time secondary is going to be less than the primary voltage. Okay, we can either step it up or reduce it, so we can change voltage with these things. And if you think about it, it's not too hard to think about what could you do. Well, what you can do is have either more coils in the secondary or less coils. If you put more coils, you get a greater change in flux. So if I come along here and I have like 3 or 4 coils or whatever, 4 coils in the primary, and I come over here and put a whole bunch of coils over here, well, the magnetic field created by this one is now going through a whole lot more of an area over here, right? We have that whole flux linkage, and you end up with a greater and a higher flux through these through over here because there's more area for it to go through, and we can step it up and get a, and this would be a step up, right? If this is the primary and the secondary, this will step it up and we'll get an increase in voltage here, right? The voltage will be higher over here than the voltage over here. So we'll have a little voltage here in the primary, and the voltage in the primary will be less than the voltage in the secondary. So that's a step up. A step down would be more like, you could imagine, if we had our 4 whatever coils here in the primary, what we'd have here is we could have like maybe 2 coils or something. And now we have more magnetic field through a lower area over here. Here's our secondary. And here, the voltage in the primary would be greater than the voltage in the secondary. And this is, it makes you have higher voltages. But energy has to be conserved, and so our power has to be conserved because it's the same amount of time for both of these things. So that means that power is conserved. And remember, power equals VI, and so it has to be conserved. It has to equal a constant. That means V in the primary, I in the primary has to equal V in the secondary, I in the secondary. Okay? And if you go through and start, go through and do your whole, let me move this down, and do the whole, what's being produced here. Here's my EMF primary, EMF secondary. What is this? This is number of terms in the primary, well, negative, but they're going to cancel out. Well, negative, change in flux per unit time, right, over the number of terms in the secondary, change in flux in the secondary, that was primary, over change in time, right? We've got those two things. Well, the negatives are going to cancel, the fluxes are going to cancel, and we can end up saying that our ratio of produced things is just going to be this. And then you can go through, I'm not going to go through it all here, but you can go through and see, and you should be able to convince yourself based on this, that you're also going to have what? I mean, just divide it over. Vp over Vs, which is this, is going to be Is over Ip, right? That's just right from that equation right there, right? Because voltages are EMFs. So divide the secondary, so you have primary over secondary in voltages, and then this would divide over, you have secondary over primary here. And so this will be our result for what transformers can do. And so why do you want to do this? Why do you want to increase voltage or decrease voltage? Well, a couple examples. One, if you want to make something that has a really high voltage but a very low current, like the little stun guns, the little taser things, right, that you get. I guess these aren't stun guns, the little tasers or whatever, that you have the little electricity come across them when you push the button. They're supposed to be for self-defense. Well, these are supposed to be non-lethal. So what you want is a really high voltage and a very low current. Well, that can come from something like this. So you can put a 9-volt battery in one of these things, right? Put a 9-volt battery here, and then what you do is you ramp that voltage up from 9 volts to your primary, and you use a step-up transformer, right? And you ramp that 9 volts up to something like, say, 30,000 volts. And so if you look at this, you end up with a very small primary and a huge secondary voltage, and look at what that does to your current. That's a small number over a big number. That means you're going to have a very small secondary current. And so that means that your primary current, whatever it happens to be, is going to drop down and you're going to have a very, very low, with that big of a change, you're going to have a very low secondary current, because current's really what's dangerous, and that's what's supposed to make these non-lethal. You have a big voltage, so even if you have to shock your attacker through their thick coat, it'll still work. But a very small current, so it won't actually stop their heart or kill them, because current is the dangerous thing. So really high current, low voltage. The other playing is through power generation. So what you can have is your power station. They produce a very large amount of current. Well, current, if they send it down the wires, what they do is they send it down these not the telephone wires, the power lines, right? So you have your power lines, and they have to send it down the power lines and ultimately over to your house, right? There's a house, a door, some windows, okay? It has to go to your house. Well, if they send this really high current, they produce this high current here, right? And it's a high voltage as well, but if they send this current down the wire, current is what creates a lot of heat. And heat is work, and work is a transfer of energy. And so this high current produces high heat, and then a lot of your energy is radiated off as heat to the environment. And a lot of the energy that's produced doesn't make it to your house because this heats up and it heats the air, and energy is lost, power is lost. So what they'll do is they take this and they put it through a step-up transformer. So they put a step-up transformer here. That's an S and a U, right? A step-up transformer. And they step the voltage up really, really high. And then it drops the current low. Now, don't get me wrong. The current here is still high enough to kill you, especially with such a high voltage. Don't go touching these thinking, oh, they have a high voltage and a low current. It's still way more than enough current to kill you. But it's so they produce a high voltage, high current, and what they do is they transform it up into an even higher voltage and a lower current. Not a real low current, but a lower current. Then they send it down the power lines, and then before it gets to your house, it goes to another step down, right? Step down transformer, which drops the voltage, so it lowers the voltage and increases the current so that you have the 120 volts and whatever current you need to actually power things in your house. So you don't just have a huge voltage that would just destroy all your electronic equipment by shoving too much current through them, and it would break all your stuff. But it'll lower it back down now here where you can use it. That's why at times like when we're here, you get like a hurricane or some sort of natural disaster where some neighbor loses power, and you hear about this a lot. It's dangerous to do, and what will happen is a neighbor will say, hey, I still have power. The light bulbs are still on here, ding. And over here his neighbor is without power, and what they'll do is they'll run an extension cord or two over to this guy, and they'll say, hey, just use this extension cord, and then this guy starts running everything in his house, so now he's got power, and he starts running everything off this one extension cord. But this is after the transformer, which means through this you have a lower voltage but a much higher current coming through it, right? And this is not designed to take that much current. So what will happen is they'll hook their extension cords together, maybe even one or two extension cords together, run it across here, and this has too high of current and it gets really, really hot and it becomes a fire hazard. So don't do that. It's dangerous. You can't run someone's whole house off that one extension cord because at this point the current is so high it produces too much heat and it can start a fire. So that's why they say you shouldn't really do it like that. This is also used in welding. You can use a step-up transformer to ramp that voltage up really high and really force electrons across and create a welder and create a lot of heat and do that same sort of thing. So there's a lot of applications for it. There's even an application of this called a ballast that I've still never quite understood totally myself, but they're used to light fluorescent lighting. I think it must be just to regulate the current to keep it steady. And what it is it's a 1-to-1 transformer where you have the same number of primaries as secondary coils. So it's a 1-to-1 where the voltages are the same. The only thing I've ever been able to think of that is it must just, because there's something in here called inductance that works, and it must really just keep that voltage really nice and steady to allow for the light to actually be kicked on and start, because fluorescent bulbs take a lot more power to start and light up than they do to just keep them on. Once you get them on, they run, but when you first push them on, it takes a big kick to first start them off, and I think you get that from doing this, but it's a 1-to-1 transformer called a ballast. And that might be a little beyond what we did, but as far as I can tell, all that does is kind of just regulates it, and it must just keep that current real high to kick it off and get it to actually light up. Okay, I think that's pretty much everything for this video. Hopefully it made a little bit of sense. If not, watch through it again or ask me about it in class. All right.